Okay, in this video we're going to try to let the Stokes' theorem do for the curl of f what the divergence theorem did for the divergence of f, which was give us some physical interpretation to what it means. Now it's a little bit more complicated with curl because divergence was a real valued function. Curl is a vector valued function, so we're not actually integrating that. That's not our integrand. We're integrating the dot product of curl with n. So what we're going to do is use Stokes' theorem to get an interpretation of what curl of f dotted with n is, and then use that to try to understand what curl is. Okay, so here's the basic setup. I'm going to have some point in 3 space, okay? And I'm going to let S sub A be a disk of radius A centered at P naught. Now, by specifying that it's a disk, I'm specifying that it's flat, that it's a round subset of some plane, but centered at P naught. And then C sub A is going to be the boundary of S sub A oriented positively. What I'm not specifying, so if the tip of my finger is the point P sub A, I'm going to be putting the disk so that its center is there. I'm going to let the pencil represent the normal vector, okay? Now what I'm not specifying is how I'm orienting the disk. So I'm not going to move it around to put it at a different location, but I could orient it this way, I could orient it this way, I could orient it this way. So what I'm going to do is I'm going to vary which plane it's a portion of, and I do that basically by varying the direction of the normal vector. Notice if it's a disk so that it's flat, the normal vector is constant over that entire disk. Okay, so I'm keeping the center fixed, and I'm just varying how I'm orienting that disk, so I'm varying what the normal vector is. Okay. Now, ordinarily, when we work with line integrals like this, we think of f as a force field, and then the meaning of this integral would be a work integral. This is another situation where it's a little bit easier to understand what's going on physically if we work with fluid flow instead. So I'm going to let V be a velocity field for some fluid. Okay, so some fluid that's going to be flowing around. And maybe we're looking at the top of the surface of the water on a river. Or maybe we're measuring what happens, 3 feet down. Something like that. Okay, I am working with a surface, which is 2-dimensional. I'm not working with a volume, okay? And I want to try to understand then what this means, and then what this means. Okay, so if I look at the integral around C of V dotted with T ds, this would now be a component of my velocity, and let's say maybe we were measuring that in meters per second or something like that. Okay, so if I just look at the units for that component of the velocity would be the same as the units for the velocity, so that would be meters per second. ds, that's arc length, so if I'm measuring length in meters, that would be meters. So the units that I'm getting are square meters per second. So it's measuring area per unit of time. And when we've got that, we call this integral the circulation. Essentially what's happening is if my vector field is causing things to spin at all, then some of the liquid, rather than just flowing past, will sort of spin around, and it's measuring the amount of area of liquid that's going to get caught spinning around. So I can sort of think of it as, if I take this disk, if I think of this as a paddle wheel, and I put it into the river, it might spin. But if I orient it a certain way, it might spin faster or slower or something like that. So this integral is going to essentially give me something that's bigger if it's spinning faster, and smaller if it's spinning slower, even though the units are actually just the amount of water that would be circulating around in this small area here. Okay. So If I now take a look at this, if we're saying that the double integral of s of curl of, I'm going to write it as v now, because again I'm thinking velocity, dotted with n ds, if that's equal to circulation, I can then take a look at what does that mean that curl of f dotted with n actually means. And what I'm going to, or curl of v rather, what I'm going to do is I'm actually going to just approximate this as the double integral over s of curl of v at p naught dotted with n ds. So curl is a vector field, it's a function, but I can evaluate it at that point. And we're supposing that that disk is going to have a fairly small radius. We're eventually going to be taking the limit as that radius shrinks to 0. Okay? So if I'm working on a small disk and curl has continuous component functions, it's not going to change too much. So it's approximately going to be the value that I have at the center. And remember, we said since we're working with a disk, n is constant. Well, if I make this whole thing constant, this would equal curl of v at p naught dotted with n times the double integral over s of 1 ds. So that would be the curl of v at p naught dotted with n times the area of s. But this was equal to our circulation. So if I solve for the curl of v at p naught dotted with n, now I've approximated it, but what I'm getting then is circulation divided by area, and we call that circulation density. It will be linked to how fast that paddle wheel is going to be spinning. If I take a look at the units for that, we said circulation was like a meter squared per second. Area would be like a meter squared. That looks kind of weird because I'm just getting something per second because the meters squared cancel. But what I'm getting is a ratio. Okay. So if I have a disk that's this big and half of its area is getting caught and spinning around in here, then that puts into perspective how much it's spinning. That's going to be, it would be spinning faster if 3/4 of the area was getting trapped and spinning around in this area. So if I think of that as a ratio of areas, I think that's a little bit more helpful. Okay. So this is just sort of approximating things, but we can actually formally define what curl of f dotted with n is, because I can say curl of v at p naught dotted with n is just going to be the limit as a goes to 0, as I make the radius of that disk smaller and smaller and smaller of the circulation, which was this integral, divided by the area, which would just be pi times a squared. Okay. So curl dotted with n is defined to be circulation density. Okay. All right. Now, when we looked at the divergence theorem, we looked at this very cool informal argument in div grad curl and all that by H.M. Shea that suggested why the plug and chug definition for divergence, del dotted with f, was equivalent to the here's what it means version of divergence, which was that it was flux density. Highly recommend that book. They have a similar argument for showing why this definition is equivalent to the definition of curl. Now, granted, this is defining curl dotted with n, okay? But this definition is consistent with the definition of curl as just del crossed f. And they've got a great argument in that book. Highly, highly recommend that. In the interest of time, I'm not going to work through that argument here. But what I do want to do is, now that we know this, let's take a look at what the curl of v at p naught really means. Because this is dotted with n, okay? So this is a vector, so it's going to have a magnitude and it's going to have a direction. Okay. Well, remember that when I take a dot product, which is what we're doing here with curl of v and n, curl of v at p naught dotted with n is just the magnitude of the curl of v at that point times the magnitude of n times cosine of theta, where theta is the angle between those. Of course, n is a unit vector, so this is just 1. So this is going to give me the magnitude of curl of v at p naught times cosine of theta, where that's the angle between the curl of v at p naught and n. Okay, so remember, this is going to be at its biggest, so the circulation density will be the biggest if cosine of theta is 0. But if cosine of theta is 0, that means that the angle between n and the curl of v would have to be 0. They're pointing in exactly the same direction. Now remember, we were sort of varying where we put n. We were saying, oh, let's put it in this way, see how fast it spins, then let's put it in this way, see how fast it spins. We were varying that. We can't vary the curl of f at a point. That's defined by the vector field, okay? So what the direction is this is the direction in which circulation density is maximized. Which essentially is, if I manage to put that paddle wheel in so that the normal vector is pointing in the direction of curl of v, that's the direction in which it's going to spin the fastest. Okay. And the magnitude, well, once I pointed in that direction, this is 1, this is the circulation density. So the magnitude is the maximum circulation density that we can get. All right, excellent. So kind of nice to have both the plug and chug, this is how you calculate it, and the here's what it means. And this is a little harder to wrap our brains around, I think, than some of the other things that we've had. But it basically has to do with how much is the vector field causing things to spin. And that's why it's called curl.